Okay, young students of chemistry, this is a recording on nuclear chemistry. Now, nuclear chemistry is a difficult thing. Like, we're talking about really extraordinary mathematics to really comprehend nuclear, but what you need to know is pretty simple. But I want you to know that this, nuclear chemistry and nuclear reactions are things that are very complex. I don't want you to think that just it is nuclear chemistry. This is what the state of North Carolina requires you to know in your first year chemistry class, which quite frankly, in my opinion, I don't think this is appropriate for a first year chemistry class. I think leave nuclear out of it. But anyway, here we are on nuclear chemistry. So what I want to start with is the differences like between real chemistry and nuclear chemistry. So what's the difference between a nuclear reaction and a normal chemical change? So why does nuclear decay occur? So first of all, nuclear decay occurs when an isotope is too heavy. So if we have a really heavy isotope, it's got way too many neutrons. That's when nuclear decay occurs. So too many neutrons. Making that isotope really fat and heavy. So this little diagram here is showing us what is called the band of stability. When the number of neutrons and the Z number, the atomic number, approach 1, so when neutrons compared to the atomic number, when that ratio is 1, that isotope is stable, meaning like the number of neutrons is equal to the number of protons. If you get too many neutrons, that's when you get out of this zone of stability and elements start to undergo nuclear decay. So nuclear reactions versus normal chemical changes. So here's the thing that we really don't want to get into here, but maybe we should, is that neutrons and protons and even electrons are made of smaller particles that are called quarks. There are up quarks and down quarks and fragrant quarks. There's all sorts of quarks. But make up protons and neutrons. And the quarks that make up the protons and neutrons rearrange themselves. Okay? So when they rearrange, they turn into different particles. So like protons are typically 2 up quarks and a down quark. Neutrons are typically 2 down quarks and an up quark. And then sometimes those will rearrange to make beta particles or helium, alpha decay. So these rearrange to make alpha particles. And electrons, really. So in normal chemical reactions, normal chemistry is really just about the electron cloud. The electron cloud, we have electrons bumping into each other from other compounds and reacting. So nuclear reactions really about quarks rearranging themselves. Normal chemistry, the chemistry that we see happening around us all day, is about the electron cloud. So just so you know, that's the difference there. Okay, let's talk about the types of nuclear radiation. These are the types of particles that can come out of a nucleus. We have an alpha particle, and the symbol is the Greek lowercase a. A beta particle, and that symbol is the Greek uppercase B. And then a gamma ray, which is a Greek symbol for, it's the uppercase gamma of the Greek alphabet. So an alpha particle has mass and charge. It's really a helium nucleus. So the helium nucleus has a mass of 4 and a nuclear charge of 2. So positive 2 is that nuclear charge. A beta particle is really an electron. So that electron has a mass of 0 and a charge of -1. And a gamma ray is just a really high energy wave. So it doesn't really have any mass or charge. It's just energy coming out of the nucleus. In terms of strength, alpha particles are the weakest, and they are shielded just by paper. A piece of paper will block an alpha particle. Beta particles can be blocked by about a half a centimeter of lead. So lead is kind of a really thick element and heavy element. It's pretty dense. So it can be blocked by lead. And then a gamma particle would require much more, a much greater thickness, a gamma ray of lead. So it's terms of weakest to strongest in terms of the particle strength. Okay, so other nuclear particles, like these don't make any sense. So it's kind of like Santa Claus, like much. Okay, so other nuclear particles, a neutron obviously, we know that neutrons have no charge and a weight of 1. So the neutron, that one makes sense. A positron does not. A positron is a positive electron. Santa Claus. A proton makes sense. A proton is just a hydrogen nucleus, right? So a hydrogen nucleus only has 1 proton in it. So this would just be the nucleus of a hydrogen, which is got a mass of 1 and an atomic number of 1. So it's really just kind of the positron that's like Santa Claus. Don't think about it too hard. Okay, let's talk about decay series or nuclear reactions. We write nuclear reactions, and sometimes you're going to be expected to predict what's called a nuclide. A nuclide is the element that comes out of a nuclear decay particle, or maybe is participating in it. Sometimes you'll be asked to predict the type of radiation. Here's the important thing to remember, you guys. We know that in chemistry, mass is conserved. Mass does not change. That is a chemical law. So even nuclear chemistry has to obey that law. So here's the thing. These have to equal each other. The mass on this side of the reaction has to equal the mass on this side of the reaction. So we're going to add those masses together. So what we're going to do is just look at this, and we're going to say, if we have a mass of 226 and a mass of 226 in the products. So these are reactants to the left of the arrow. These are products. We know that that mass did not change, so whatever that particle was that was given off, have a mass of 0. And then what can we add to 89 to get 88? And that number is going to be -1. So when you see that, you go, hey, I learned in my notes that that's a beta particle, that this is an electron, that this is beta decay. This nucleus has spit an electron out of it. Santa Claus, don't think about it too much, because the electrons are not in the nucleus. Okay, so we have another one. This time we're told that this is what's coming out of it. This is an alpha decay. And we have to predict the nuclide that's formed. So we need a number that we can add to 4 to get 209. So what number do we add to 4 to get 209? And that would be 205, right? I hope you're kind of thinking this through as we go. What number do we add to 2 to get 83? And that would be 81. Now here's where you pull out your periodic table of elements, the tool for your mind. You should always have. So you're going to look at your periodic table, and you're going to find element number 81. Element number 81 on the periodic table is thallium. So you're going to put in the TL symbol, indicating that that is an element of thallium. I don't know what that is. Maybe erase that. Okay, so the nuclide form is thallium 205. Remember, the bottom number here is always the atomic number. So we can also do this in a series. This is the beginning of the decay series for uranium. Uranium is the radioactive element that we get our electricity from, or we get our power from. So here we have uranium-238-92, helium-42. What's the nuclide formed? What number can we add to 4 to get 238? And that's going to be 234. 234 plus 4 makes 238. Let me just, 234 plus 4 makes 238. Okay, so what number can we add to 2 to get 92? And that is going to be 90. Then we look on our periodic table and we say, hey, what is the element that has an atomic number of 90? And that is thorium. Now we have a new nuclide, a thorium nuclide, and it's going to undergo a beta decay. This is beta decay. The mass does not change, so 234 minus 0 is 234. And then we have to do 90 minus negative 1, which is really 90 plus 1, right? And that takes us to 91, which is, I better look this one up. Sometimes I get, protactinum, PA. I didn't want to put PR. So now we have this new nuclide, the protactinum. It's going to undergo a decay which produces uranium again. So we have to pick the type of decay here. What do we add to 234 to get 234? That is 0. What do we add to 91 to get 92? That is negative 1. 92 plus negative 1 gives us 91. So that's going to be a beta decay. So what's happening here is that you can see that the uranium's getting more stable because the weight has already gone from 238 to 234. So the weight is going down. So it keeps going closer and closer and closer until it gets a stable nuclide. So now the uranium is going to undergo a decay here, which produces this thorium, 230 over 90. So what type of decay is it? We're going from 234 to 230, which means that's a difference of 4. And we're going from 92 to 90, so that's a difference of 2. So this decay is an alpha particle. And then we would do this so on. You'll have a problem set to practice this. But we have 230 now, thorium. And now that thorium-230 is turning into thorium-230. It's not changing at all. We have 0 change in the mass, 0 change in the charge. So what we know is that that's a gamma ray that's been given off here. So gamma radiation is really high radiation. It's really very energetic, very dangerous to be around. So that's a gamma ray that has come off that. Okay, the two types of nuclear, we call it transmutation. Nuclear transmutation are just the types of nuclear reactions. We have fission and we have fusion. You can see the diagrams here that fission is the splitting of a usually very large nucleus. So the splitting of, I'm just going to put usually, because sometimes it's not, very large nucleus. Okay, so it's usually a very large and unstable nuclide that's splitting, and that is what is occurring in our nuclear reactors. So our energy the nuclear energy that we get from Duke Power, This is the reaction that's occurring in our nuclear reactors, a fission reaction. Typically we bombard an unstable nucleus with a neutron, and that causes it to start breaking apart. Fusion is where smaller nuclides come together to make a larger one. So typically the nuclides that do this are hydrogen nuclides. You guys, this is fusion, nuclear fusion reactions are those reactions that are occurring in the sun or in our stars. The reason there's all that light is because there's all this energy from the nuclear fusion reaction. So here's just a little introduction to nuclear chemistry. We're going to talk about half-lives in class. So if you printed these notes, you will see that these notes go along with the half-life. There's half-life on there as well. We will get to that in class. I think it's important that we do those together. But this information I thought you could get without me. So here you go. Thank you very much. We're done.